Hello and welcome. I'm Dr. Syed Mostafa Safavi, and you're listening to our podcast series on deep learning for intrusion detection. In this series, we explore how cutting-edge AI techniques are reshaping the way we detect and respond to cybersecurity threats. This podcast is produced with the valuable support of Alicia Tan, who has been instrumental in coordinating and preparing each episode. Now, let's get started and dive into today's topic. Welcome to our conversation on deep learning applied to intrusion detection, cybersecurity, and the underpinnings of modern machine learning pipelines.
I'm really excited to dive into that. So, we're looking at how ML methods are being implemented to tackle cybersecurity challenges, right?
Exactly. It's like we have a whole spectrum here, from user behavior analytics and endpoint protection to extended detection and response, which also leverages ML pipelines.
Right, and it's amazing how these systems use unsupervised learning to untangle complex behaviors, isn't it?
Absolutely. It's like trying to sift through a massive logbook of user actions, social networks, messengers, and all those different account types, and using clustering for peer group analysis or anomaly detection on unusual login times.
Exactly. So, in essence, we're monitoring both domain and application user behavior by grouping them and then flagging any out-of-the-ordinary actions.
Yes, indeed. And then if we pivot to endpoint protection, ML algorithms are at work classifying programs into their respective threat types: malware, spyware, ransomware, you name it. It's like having an intricately layered system that not only detects but also responds to these intrusions.
I get that. And Endpoint Detection and Response, or EDR, plays a crucial role by monitoring system-level behaviors, right?
Right. EDR systems record and analyze endpoint activity, block malicious actions, and even offer remediation suggestions. It's a comprehensive approach that doesn't just rely on signatures, but also heavily on behavioral analytics.
And that ties in well with UEBA, User and Entity Behavior Analytics, which uses both basic and advanced analytics, correct?
Exactly. UEBA creates profiles from telemetry data, using simple rules like pattern matching alongside advanced ML techniques to spot anomalies.
Yep. Now, what about XDR? I've heard it's sort of an evolution of these systems. How does that blend in?
XDR, or Extended Detection and Response, is essentially combining the power of NDR, UEBA, and EDR. It uses machine learning and dynamic analysis to stitch together logs from third-party sources. It's like having an integrated view where ML is constantly absorbing unique organizational patterns to differentiate between legitimate and malicious activities.
And the reliance on third-party logs must add another layer of complexity, right?
Definitely. The richness in data coming from multiple sources, network traffic, endpoints, even cloud instances, enables XDR to correlate patterns effectively. It's almost like assembling a giant jigsaw puzzle with pieces from everywhere.
Yeah. Speaking of assembling puzzles, I noticed that the discussion also covers state-of-the-art NLP for cybersecurity, like using unsupervised machine learning on logs to do root cause analysis.
Oh yes, that's a really fascinating part. It's kind of amazing. By automatically clustering correlated anomalies across log streams, these systems can pinpoint the root cause of an incident in under 24 hours.
It's almost like giving you an instant diagnosis when applications break, without having to manually comb through all the logs.
Right you are. It significantly speeds up troubleshooting and reduces downtime.
And underneath all these advanced analyses, we have the core machine learning fundamentals like regression and classification, right?
Correct. The material goes into detail about supervised learning tasks. For example, in classification, the models predict certain categories, like which programs are malware, using algorithms such as logistic regression, decision trees, or random forests.
And then there's regression, which predicts continuous outcomes. I saw an example relating cigarette consumption to coronary heart disease mortality.
Exactly. Regression analysis just quantifies the relationship between a dependent and independent variable. It's crucial when you need to predict something like risk levels from continuous data.
Right. But here's something I'd like to challenge a bit. Don't you think that sometimes the simplicity in regression models can miss out on capturing nonlinear relationships?
That's a valid point. I mean, while simple linear regression gives a good baseline, sometimes the relationship is more complex. And that's where models like decision trees or ensemble methods step in to bridge those gaps. It's a trade-off between interpretability and predicting power.
I see what you mean. Absolutely. And the conversation on ML really dives deep into the nuances of these trade-offs, doesn't it?
It does. Beyond just the algorithms, the discussion goes into the terminologies, features, targets, training examples, loss functions, the whole shebang of constructing a model.
I found it interesting how the content delineates the steps in an ML pipeline. It's like a well-orchestrated process from data collection to model validation.
Yep, the pipeline is iterative by nature. It starts with defining the problem, then moves on to collecting data, which, by the way, must be representative of the population. Then there's feature extraction, where you choose which variables to include.
Right, like reducing dimensions and dropping unique identifiers. And following that, data preparation is crucial, isn't it? Normalization, scaling, and even the creation of dummy variables to ensure that the data is in the right format for the model.
Exactly. Each step plays its part. Next comes algorithm selection. It's interesting that there's no one-size-fits-all algorithm. You have to experiment based on the problem statement and domain knowledge.
Then the performance evaluation kicks in. You fit the models, compare confusion matrices, and decide which algorithm performs best.
True. And after this comes model validation. The goal here is to check for overfitting and refine hyperparameters, typically using methods like grid search or k-fold cross-validation.
Speaking of hyperparameters, it's intriguing how these factors are tuned to optimize a model's performance while maintaining generalization on new data, right?
Yes, it's almost like tuning a fine instrument. You need the right balance of error tolerance and iteration count to capture the signal without overfitting the noise.
Yeah, and then, to top it all off, there's that iterative feedback loop, where the insights from model evaluation might lead you to refine your feature extraction, or even choose different algorithms in the next cycle.
Precisely. It's a continuous cycle of improvement, and as we iterate, we get closer to a model that provides robust and accurate predictions in the face of ever-changing data, especially in cybersecurity, where attackers evolve their techniques.
Right. It's fascinating how all these layers, from the basic stats and linear regression to the complexity of XDR and NLP, work together to keep systems secure.
Absolutely. And just think, these models aren't static. They learn over time, adapting to new threats and uncovering hidden patterns across vast data sets.
Indeed. I think this integration of advanced ML with cybersecurity really highlights how cross-disciplinary approaches can provide newfound resilience in our digital ecosystems.
Yes, and it really shows that by combining rigorous ML methods with real-time data collection processes and iterative pipeline improvements, organizations can proactively detect and respond to ever-evolving threats.
Exactly. It's kind of like a well-drilled team that keeps refining their playbook after every game.
Right. And as a final thought, what stands out is the balance between using classical methods like regression and classification and integrating modern techniques like unsupervised ML for root cause analysis and dynamic threat detection in XDR.
Yep, that balance is crucial. Well, this has been a thoroughly engaging discussion. I've learned quite a bit about how deep learning and ML pipelines intersect with cybersecurity in today's tech climate.
Absolutely. It's been fantastic to explore these concepts. Each element builds towards a system that's not only reactive, but intelligently proactive in stopping threats before they cause harm.
Thanks for the deep dive. This conversation certainly highlights how intricate and vital these ML techniques are in safeguarding our digital world.
Exactly. Until next time, keep questioning, keep exploring, and keep innovating in this rapidly evolving field.